Example 4.7, a sled on a frictionless hill. A sled is tied to a tree on a frictionless, snow-covered hill. If the sled weighs 77 newtons, find the magnitude of the tension force T exerted by the rope on the sled and that of the normal force N exerted by the hill on the sled. Before we start on this problem, I want to talk a little bit more about a geometric figure. And imagine a triangle that looks like that, and another triangle with, I probably drew this poorly. I want to draw a straight line down and a line. This line is parallel to this line, and this should have been a right angle. Okay. So if I have this angle here, theta, and this is a right triangle, then what can I say about this angle here, theta prime? It is the sum of the internal angles of a triangle are 3, 2, 1. Okay, so we have been given this angle with the horizontal, which I will call theta. And we know that there's basically two forces acting on this sled, three forces. We've got gravity acting downward. I want to draw that as a straight line. And that force is mg. We've got a normal force, and the reason, and it's called normal, it's perpendicular to the surface of the sled. So that is the normal force. And then we've got the tension acting this way. And I want to talk a little bit about angles for a second. First of all, I'm going to draw another line that follows the normal force coming this way, and another line that follows the parallel surface. And that's basically what the idea of the normal force is. It's perpendicular to the parallel. So I'll rewrite this mg over here so that we can kind of separate those things out. Mg is going to be separated out into two parts. And it's going to be based on this angle here. But what is this angle here? The quick answer is it's theta. But let's see if we can reason out why that is, that it's theta. First of all, this is a right triangle here, and this is a right triangle here. So if we add, let's see, and this, let's call this angle theta prime. So this angle is theta prime, and we can see that theta plus the 90 degrees plus theta prime, and the internal angles of a triangle are 180 degrees. That has been shown. We can also see the 90-degree angle plus theta prime plus this gives us this straight line here. So this is going to give us 180 degrees. So since this plus this is 180 degrees, and this plus this is 180 degrees, we know that this is also theta. So that means that this vector is going to be mg sine theta. That's the force of mg in the parallel directions. And the force of the mg in the normal direction is mg cosine of theta. This is the force of gravity on the sled that opposes the tension, and this is the force of gravity on the sled that opposes the normal force. So we can say the magnitude of the normal force is mg cosine of theta, and the magnitude of the tension is mg sine theta. We weren't given the mass, though. We were given the weight. So weight is mass times gravity times cosine theta, and weight times sine of theta, which come out to be 38.5 newtons for the tension and 66.7 newtons for the normal force. If you put the sled on a steeper slope, the magnitude of the tension in the rope would get smaller, or would get larger. Yeah, the tension in the rope would get larger as the sled hung down a steeper slope, and the normal force would get smaller. In Quick Quiz 4.6, for the woman being pulled forward on the toboggan in Figure 4.16, is the magnitude of the normal force exerted by the ground on the toboggan A, equal to the total weight of the woman plus the toboggan, greater than the total weight, less than the total weight, or possibly greater than or less than the total weight? Okay, the key to this problem is that this man is pulling upward on the toboggan. And because part of the weight of this person on the toboggan is canceled by that upward force of his pulling, the normal force will actually be a little bit less than the total weight. So the answer would be C. So now we've done two problems where we have equilibrium. In the next problem, we will be doing something where we have motion and acceleration. And just for a little bit more detail, you recall in our traffic light situation, I said the sum of the tension in the x direction was 0, and the sum of the tension in the y direction was 0. The reason I said that was because we assumed that the traffic light was not under acceleration. In this problem, I didn't go into it in as much mathematical detail, but I assumed that the mg sine theta was canceled out by the tension, and the mg cosine theta was canceled out by the normal force. So n plus mg, or yeah, n going up plus mg cosine theta going down equals 0. Mg sine theta pulling the sled that way plus the tension pulling that way is 0. If any of those had not been 0, then the sled would have been under acceleration.